Hello everyone and welcome back to another video here at the Hidden Quantum Champions. Today we are checking out SemiQon with a Q, which is definitely one of the hidden champions in the Nordics of Europe. And if you want to know what they're actually doing with silicon and quantum dots, then stay tuned for today's video because now we are deep diving into SemiQon. And with that, let's hop right onto their website. So here we are on the website of SemiQon with a Q. And you see this like wavy, fancy looking background image here. And it says, we build quantum processors for the million qubit era. Real, scalable, cryogenic ready quantum hardware available now. So million qubits, that's quite a lot, because if we are looking at today's biggest chips, they are usually in the hundreds of qubits. When I started, there were only 2 qubits on the first chip that I worked with, which for physicists is already enough, because you can do both superposition and entanglement. But in order to build useful stuff, you really need a lot of qubits, because you need to put the error correction code probably on those. So you need thousands and thousands of qubits, because you already need tens of qubits to make a lot of physical qubits into one logical error correct qubit. So you need millions to really build big applications. So this is a bold statement, and let's try to learn how they actually want to achieve that. So it says, we develop silicon-based quantum processors to make future quantum computers more affordable, scalable, and sustainable. So silicon technology, which is a mass technology, it's what's being used in today's chips for computers, smartphones, smartwatches, whatever you want to think about, washing machines, everything is based on this silicon technology. So if you could figure out a way to use the same technology to build quantum chips, you could basically, let's say, sit on the shoulders of these giants and just use the existing knowledge about semiconductor manufacturing to build those chips. Of course, besides that, there are also other challenges. I'm not sure if we will talk about these in today's video, but let's say this is the purely chip scaling side of things. And we could click here to learn more about the technology, but we will not do that for now. We scroll further down. So our mission is to power the scale up of quantum computers with silicon-based quantum processors. And then here are the products. So we see SemiKit, fast track your quantum research with reliable silicon quantum dot devices. So I guess this is, let's say, the chip part of it. Then there is SemiQon Cryo CMOS, explore the world's first transistors fully optimized for cryogenic conditions. And this is actually something that I was talking about before. So that touches on this topic. Today, we have these chandelier looking like cryostats, right? So you have the chip sitting at the very bottom, and then you have the different stages on top of it. You see all of these cables going up, the radio frequency lines and all of that. The problem is with these systems that on the top you put in kilowatts of electrical energy to kind of create this cooling power, but as you move down stage by stage, the cooling power gets less and less. And the lowest stage, I think, is usually in the microwatts of energy, of cooling power. So there's only a tiny little bit of heat that is really being transferred away, which is enough to go down to like 10 millikelvin, but only if you don't put too many cables on there, because the more cables you add into this cryostat, the more thermal bridges you are building, the more connections you have. This is very similar to everyday life, right? So if you have, let's say, less thermal connection, if you have windows where there's like some gas filled in between that doesn't have a lot of, so you have these windows with 2 glasses and you have this gas in between that is very well isolating. This is working pretty well, but as soon as you kind of remove the gas and you put, I don't know, liquid inside, suddenly the situation is completely different. And the same is happening here. So as you add more cables, you add more heat transfer from room temperature to these lower temperatures, and this is just not scalable. So at some point you're running into this issue that you cannot add more cables, but you need to have these cables because you need to control more qubits. If you want to have more qubits, you need more electrical control signals. So at some point you need to kind of move down your electronics into the system itself. So like you need to move the control electronics into the cryogenic stages, or you need to be able to kind of build bridges between those chips. So these are two different paradigms that are being also followed on the research side. So either you have multiple of these, let's say, smaller chips at lower temperatures and you build quantum connections between those, or you kind of move cryogenic electronics down. And this is what this cryo CMOS here is about. CMOS is the standard silicon technology that is being used in today's manufacturing to build chips. And usually the problem with that is it's not made for these low temperatures. So even in your smartphone, there is an operating temperature range. And if you go down too much in temperature, the transistors, they don't work anymore as they are supposed to. They become insulators. And that's why it's very challenging to build electronics that works down at these cryogenic levels. And that's the long story short to tell, okay, this is kind of a proposed path towards building a solution to scale up the number of qubits in these chips here, because if you were to move the electronics down to the cryogenic stage, you can, let's say, reduce the cable load as you also reduce the cooling power of your cryostat. So basically using the different stages in your chandelier to reduce the number of heat load, the amount of heat load that you carry down. And then finally, there's the SemiQon quantum IC chips, so silicon-based QPUs, quantum processing units for scalable, sustainable quantum computing. Finally, there's some video here. I'm not going to click on that, as well as some news articles. I'm recording this beginning of 2026. We see here this announcement about ESA, Business Incubation Center in Finland, and SemiQon working together on a project, which is pretty actual because, I was only, this is only being recorded beginning of 2026. There's also something about media coverage. Here we see December 2025 in IEEE Spectrum. There is some coverage here, but you see also some other media covering them. And then, of course, the call to action. If you want to learn more, you can subscribe here to their newsletter. With that, let's quickly move up again and check out their technology. So we develop silicon-based quantum processors to make future quantum computers more affordable, scalable, and sustainable. The technology is this silicon-based technology, right? So at SemiQon, we are solving a problem everyone in the quantum business is desperate to solve, scaling up qubits in an affordable and sustainable way. Our silicon-based quantum processors or quantum integrated circuits can be manufactured using affordable standard semiconductor manufacturing materials, tools, and methods. We started SemiQon to build a technology that can overcome the biggest challenge, solving down the progress of the quantum industry, the scale of quantum computers. As we develop and design our technology, we do this with the million qubit era in mind. We build processes to power the next era of quantum computing, but while doing so, we are solving engineering challenges that will benefit the industry as a whole. We aren't afraid to say that we don't aim for one of a kind. Our goal is to build productized and affordable, high-quality silicon-based processors that can power the scale-up of quantum computing globally, not one single piece of exceptional hardware. And then there's another video here and the products that we've seen before, as well as some close-up shots of the chip itself. And then it says quantum integrated circuits, QUICs on silicon, and approach that makes sense. Why quantum integrated circuits? Reverse the unsustainable trend of expanding control electronics by integrating the control logic system onto a chip inside a cryostat, eliminate the cabling bottleneck with on-chip routing on the QUIC, enabling millions of times higher packaging density and sustainability. That's what I was trying to kind of explain before. And then significantly reduce infrastructure costs, avoiding cost associated with quantum computing, and this is kind of catering, I guess, towards the whole electronics, control electronics, and so on. That is out there. The most promising way to realize cryogenic multiplexing control and or read out of qubits is cryogenic CMOS electronics, so cryo CMOS. That's what we were talking about before, right? Using the same process to fabricate both qubits and CMOS circuits on the same chip, the ultra-low charge noise background limiting spin qubit performance due to spin orbit coupling or of QD qubit devices at high temperatures above 1K was demonstrated. We aim to extend cryogenic multiplexers to accommodate hundreds of spin qubit devices on a few millimeter silicon chip and apply recently developed machine learning algorithms to allow for automated de-extraction of electronic and spin coherence properties of qubit arrays with the same cooldown. So here's kind of the integrated QPU solution. So you have so this is the roadmap. So you have the cryo-optimized transistor, which they developed in 2024, low charge noise quantum dots. So there's always these two paths here, the cryogenic CMOS and the spin qubit development. And in 2024, they made the first transistor that actually worked at these low temperatures, as well as the first low charge noise quantum dots on their chips. Now in 2025, so this was last year, it said low VDD cryo circuits. So this is now the first, let's say, logic circuits, I guess, composed of these transistors, and then a 1D quantum dot array, so adding multiple dots to each other. And the next step would be to have a scalable I/O, so I guess a scalable circuit approach and a scalable qubit element, so more qubits to build a pattern. And then at the end you would end up with, let's say, adding more and more of those circuits together with a cryo microcontroller and a 2D qubit lattice, which then leads into this integrated quantum processing unit on one chip. So our cryo CMOS transistors were its first transistors fully optimized for cryogenic conditions. Until now, traditional electronic components have typically been used in ultra-low temperatures, such as quantum computers, despite them chronically underperforming in cryogenic conditions. In 2024, SemiQon launched the world's first transistor specifically designed and optimized for function efficiently in cryogenic temperatures, engineered to perform in temperatures of 1 Kelvin and lower. SemiQon's new cryo CMOS transistor consume 0.1% of the power and deliver heat dissipation levels 1,000 times lower than traditional room temperature transistors. And then speed and price that are hard to beat. And yeah, the kind of look onto the roadmap as well. So that's about the technology. Let's quickly also check out the products. So I think we've seen them already a little bit before. I wonder if there is also some information available here. So what's in the semi-kit package? Select the spin qubit chip variants for R&D. Device shipped fully packaged. Plug and play without tedious bonding and on R&D side, quality control, technical support, and designed for university and research groups. And there are different versions of it available. So there's the SemiKit 4, 6, and 12, and the SemiKit 128M. The first three ones are fully packaged device with plug and play FDSOI nanowire with 2 gate layer barriers and plungers for electrostatically defining the quantum dots. So I think, if I understand it correctly, this is like nanowire quantum dots. So in a nanowire quantum dot, you basically take a wire that has nanometric size. So they're usually semi-crystalline crystals that are grown in some type of epitaxial process. And then you kind of harvest them. There are different ways of harvesting them. You can do it with a Q-tip, but you can also kind of go the more controlled way and harvest them with a nanotip, and under an electron microscope place them in certain positions. And then if you contact them and you put gates on top that look like fingers, you can separate them into one-dimensional quantum dots. And that's how I understand this is being done. So with 2 gate layers, so usually these are wrapped around layers that can also be done via epitaxial access, and then there's also barriers and plunger gates to kind of control and manipulate those qubits. For the 128M, it says fully packaged device with plug and play, quantum IC device with 6-bit digital multiplexer, or addressing 64 pairs of double quantum dots. The quantum dots have 2 gate layers, barriers, and plungers. Now here it doesn't really say how these are actually being produced, but maybe these double quantum dots are then already embedded into the silicon, because there are also ways to create, let's say, inside the chip itself, some quantum dots, which is something that I've also learned very early on in my quantum journey about. So there are these 2 different kind of products, and then of course there are more information here, as well as research institutions they work with. Amongst them is, of course, in Europe you see, for example, Oxford. You also see Basel University in Switzerland, but you can also see that there's international universities, like for example here in Seoul, and many others, Taiwan and so on, involved here as well. And some, let's say, statements of the customers or users they have. Let's quickly also check the Cryo CMOS part. So scaling quantum systems with SemiQon Cryo CMOS, the world's first transistor fully optimized for cryogenic conditions. By integrating qubit control directly inside the cryostat, we make quantum computers more scalable, efficient, and commercially available. There is some information about that. Here's what it looks like. So I think that's also very interesting. This is this integrated chip solution, right? So I would guess that these are, let's say, the quantum dots or the quantum systems itself. So you see, usually you write them in 2 different lithography steps. So one of them being a little bit more coarse, and then in the second one you kind of look specifically in this area here, and you use something like an electron beam lithography step to make these very, very tiny gates in here, which are being used to confine the electrons and to manipulate them to make a qubit out of that. And that's where, let's say, the more complex part of the silicon technology goes into. Here it says build on silicon, so use traditional CMOS silicon, avoiding exotic materials that require costly infrastructure. That's because if you move away from the CMOS technology, so if you, for example, use copper as a metal, or if you want to use gallium arsenide, which has been used very early on in this spin technology, you immediately run into the issue of doping your silicon, and that's what you don't want to have. That's why there's the CMOS, and that's why no big fab, like no TSMC, no Intel, no one would ever let you manufacture that in their fabs next to the, let's say, standard lines. So if you want to, let's say, play this game of using the existing fabs, you have to stick to the CMOS technology. And if you want to, let's say, know more about this, also let me know down in the comments below. Happy to make a separate video about this technology stack as well. As a strategic partner, not just a supplier, we collaborate closely with early adopters and integrate feedback into new designs, and then in-house manufacturing developed in a semiconductor pilot line, enabling speed and quality control. Why choose SemiQon Cryo CMOS? And that's, I think, something that we've seen in terms of arguments before. There's also some technical information here on the, let's say, different relevant parameters. So you see the minimum sub-threshold swing, so the sub-threshold slope and so on are very important parameters of transistors. And there you see up here, for example, the SemiQon, and then you see, I guess, some competitors or competitive solutions, and there you can really see how well it's performing, especially in the RT versus cryo ratio here. So you see For example, here the sub-threshold gain increase is 203 times, whereas for the other ones it's usually single digits. So that's why it makes sense to have this very specifically optimized components in the cryostat itself, because they work highly efficiently under these cryogenic environments. Let's quickly check out the about section as well. So SemiQon, our mission is to power the scale up of quantum computer with silicon-based quantum processors. What we do in quantum and beyond, we deliver cryogenic CMOS chips for next generation critical technologies and build silicon-based quantum processors for the million qubit era. And then there's in quantum and beyond. So in quantum at SemiQon, we build quantum processors for the million qubit era. We want to develop the technology needed to close the gap between today's reality and the future possibilities of quantum computing. Our SemiQon-based solutions respond to three major challenges that are currently slowing down the development of quantum computers globally: their scalability, price, and sustainability. Our technology allows us to fabricate quantum processors in a way that supports scaling up manufacturing efficiently while also lowering cost. The chips and controller electronics we manufacture also enable the quantum computer to operate at warmer temperatures, thus requiring only a fraction of the energy needed for alternative solutions. As we develop our solution instead of starting from scratch, we build the next revolution of computing power on decades of technology development and know-how of semiconductors that have made our current digital era possible. We benefit from an existing industry which will support the scale up and commercialization of our technology and boost European competitiveness and technological sovereignty in quantum. We see that the specialization is speeding up in the quantum field and believe that the entire industry will benefit from more companies doing fewer things. That is why SemiQon's strategy is to focus our effort on where we can bring the most value and collaborate with partners who excel at other things. And beyond, the problems that need to be solved to realize the potential of quantum can bring immediate value also in other critical technologies beyond quantum. Innovations like SemiQon's power-efficient electronics developed for extreme temperatures also have major advantages for areas such as space tech and high-performance computing. And then there's also a link here: SemiQon's cryogenically optimized CMOS transistors, or Cryo CMOS for short, enable a paradigm shift in energy consumption anticipation and could be used to address one of the most pressing challenges in high-performance compute. So basically, I guess, taking the idea of what would be if we would build computer chips that would run under cryogenic conditions where they might operate more efficiently than in today's data centers. And then of course space is also interesting, because in space you have these very cold temperatures in outer space. There it's much colder than here, and therefore if you would have these kind of transistors in a space application, they would also be more efficient or more reliable under these. Quickly on the story about the company. So a spin out from VTT. The funding team of SemiQon came together at VTT, so a technical research center of Finland, where we worked in different capacities with microelectronics, quantum, and innovation management. As researchers in the quantum field, we are constantly exposed to many expectations directed at quantum computers, from developing life-saving drugs to achieving climate neutrality. Ambitions are high, and for good reason. We believe in the potential of quantum, but also understand that overcoming the challenges of scaling up quantum computers from a handful of qubits or even a few hundred to hundreds of thousands and then millions requires innovation, commitment, and technical breakthroughs. We felt confident that our solution could offer a viable and cost-effective solution, so we decided to get to work and those breakthroughs to help realize the promise of quantum. In 2022, SemiQon got its start as part of VTT's Launchpad incubator. During the year, we worked on developing the business plan and surrounding ourselves with a group of experienced investors and mentors. In early 2023, it was finally time to kick off independent operations. We are based at the Micronova Center for Applied Micro and Nanotechnology in Espoo, Finland, and have access to a facility that allows us to carry out fast design and fabrication cycles. By 2025, we have consistently checked off business and technology milestones. We have built an extensive global network of partners, filed several patents, secured significant public funding, and launched 2 of our first commercially available products. We are proud to say that we are on track to realize the potential of quantum computing our way. And then there are some beautiful pictures of the wafers and the chips that they are making. There's also some investor information here. So our investors secured 2 million euro in funding by February 2023. Lead investor, Helsinki-based deep tech investor Voima Ventures. So by 2023 we had secured 2 million euro. And so on. I don't want to go into the details of that. What is important is in the spring of 2025, we had the pleasure to announce that the European Innovation Council 2.5 million in a competitive non-dilutive grant and an additional 15 million euro of equity-based earmarked funding. So there was another funding round going in there. Let's quickly also check in the about part if we can see something about the team. I don't want to stretch the video for too long. Also, by the way, if you find these videos too long, let me know down in the comments below. I can also cut them short, or I can make them longer if you want me to go into more details here. So about the team, we concisely, carefully continue to build a team that has the perfect combination of expertise required to build chips that will power the future of quantum computing. Our team combines seasoned experts with significant scientific contributions, hands-on experience in fabrication, and extensive experience in working with industry. Together, our backgrounds bring together the best of many worlds and allow us to create entirely new disruptive solutions. The rate at which we reach one technological milestone after the other is a testament of the remarkable skill set of our team and the way we seamlessly work together. We offer our experts opportunity to work on overcoming some complex, but if you ask us, endlessly fascinating technological challenges. To do so, we prioritize building an environment that fosters shared values and an atmosphere of mutual trust and care while striving for excellence. And then I guess here we can see the team of all the different people that are working within the company. Here's the founders team. You see CEO, Chief Science Officer, Chief Research Officer, and Director of Operations. And then there's the board and the advisory board. And here, I guess, are the values. So equality, resilience, openness, safety, excellence, trust and care, timeliness, satisfaction, and diversity. With that, I would like to wrap up today's video. I hope you liked it. If you found it interesting and if you want to learn more about these companies in the quantum space, please make sure to subscribe to this channel so you don't miss out on the next one. If you haven't seen all of the videos yet, go check out the playlist that you can find on the YouTube channel, which is the Hidden Quantum Champions playlist. You will find it on the channel. And as always, make sure to stay hydrated and see you in the next one. Bye bye.